There is this effect that is the formation of the grains of the microstructure with the introduction of hardening, and this is also seen here in this graph. It's referred to the trend of the hardness in depth, and we see that after short period, the hardness is increased with respect of the core, and with a characteristic trend, let's say that this is one. Then the trend can be with a peak just under the surface, or to peak, the maximum value can be also at the surface. But this is not the only effect, because we can see also that after the impact, of course, we have plastic deformation. The finishing of the surface will be also changed. We are introducing a different roughness. Okay, this is what we are doing. And finally, and this is the most important effect, at least for practical application of graphene, by means of this not uniform plastic deformation at the surface, we are able to introduce compressive residual stresses. Okay, that is the main aim of graphene, the ability to generate compressive residual stresses by means of this, of a mechanism that we commented yesterday, not for graphene, but more in general for plastic deformation, and make possible the generation of the trend. Like for graphene, this is the there is a compressive surface residual stresses, then the peak of compression under the surface, and then the residual stress decreases and becomes positive, but a certain depends on the short picking parameter. It's important to notice that short picking sometimes is confused with sandblasting or grid blasting, but it is a very different treatment. Sandblasting and grid blasting are used just for finishing purposes, okay, to change and to polish the surface, to make smoother the surface, but not for. And this can have also some effect on fatigue, but the main scope is not that. It's just changing the surface and finishing the finishing of the surface. Okay, why? And the media are not controlled. We have sand, grains, and so on. While in short beading, this is aimed to fatigue, let's say, and the media are strictly controlled. Otherwise, the risk is that if we do not control, we see in some minerals, if we do not control the media, the risk is that with this multiple impact, we are going to damage the surface, and so as to lose the benefit induced by the residual stress, the beneficial effect. Okay. And indeed, let's see now from a more qualitative point of view, and then we will go into the effect. What are the effects of graphene? Indeed, the effect of a single shot impact can be compared to the impact of a hammer on a metal target like this. Okay, and it's also true that someone said that the first application of short beading dates back to the ancient time, where the zoomer used to harden the sword by heating with hammer the sword themselves to make them stronger and more harder. Okay, and short beading is something like this. Each single shot can be considered as an hammer hit. Okay, small hammer hit, and the indenting of the surface of the stretch in the orthogonal inequality. That is to say, by means of short pinning, the indentation, of course, is the single indentation is circular, and so there is stretching in the orthogonal, to the interplane orthogonal to the impact direction. Okay, and so the shot is axisymmetric, is spherical or spheroidal, and also stretching, so it's axisymmetric. Okay, the single one at least. Okay. Some history. Indeed, I said that the introduction of short pinning dates back to ancient time, but if we consider short pinning as an industrial process, indeed, it was introduced in the period between the two world wars, and this was around 100 years ago now. This is to say, and the first studies about short pinning work done in Germany, where the mechanical input was well developed, and someone had the idea to initially to work out the surface due to a breakage. It is still not so clear, but it's something to go in that direction. Then some years later, found that cold hammering improved bending fatigue. This is still not so clear that it's cold hammering, but once this is understood, it's the immediate consequence is to use some other media, to say, there is a German pattern where still short lasting of treatment. So the spring was the first application, at least from a patent point of view, to be developed in Germany to improve fatigue strength. And then after that, many other studies come, many other applications, not only for spring, we know, in the Fay and Kale notices the influence of the cleaning procedure, such as sandblasting, and have also an effect on fatigue behavior, and then finally shot pinning was developed. Important to remind and to underline the work by John Almet in the US at General Motors. He was an engineer at General Motors that introduced shot pinning in the industrial cycle, in the industrial production line, to improve the fatigue strength of some of the engine part. Okay, and he also, indeed, he realized that the full application, the full exploitation of shot pinning is possible just if we find a way to standardize the way it is done in the company, in the industry. And he invented, he defined the Almen intensity. It is the usual way that is used still today to define the at least partially the parameter we are using for shot pinning. And we will discuss later. And then, after that, other evolution, other innovation were done. Some are related to the experimental tool we can use for characterize the effect of shot pinning, and I'm referring mainly the possibility to measure the residual stresses, to quantify so the effect of shot pinning, and this can be done with different methods. One attractive method, at least in both for the accuracy, but also for the possibility, because if we refer just to the survey, it is not destructive. The X-ray diffraction is a method that is widely used, but it's not the only one. We can use also the oil drilling method, some other methods that are commonly used for this kind of measurement. Okay, and then this makes possible a better understanding on the relation between the shot pinning parameter and the effect of shot pinning parameters, and then other studies came later, stress pinning, yielding. What is this? Stress pinning yield superior nature of fatigue strength. Stress pinning is an evolution, let's say, a particular application of shot pinning where we are applying shot pinning on a mechanically stressed component. That is to say, yesterday I introduced the preset or pre-stressing by showing the example of the leaf spring. We can perform shot pinning in this condition under stress. And this make possible to induce even larger compressive residual stresses. And this is for sure, it is good. Even the treatment is more complicated, of course, because we need also a tool, a device to apply the load. But anyway, this is making shot pinning even more effective. And then we go now fast to the other historical period. Indeed, from the 60s, the shot pinning was not only confined to automotive, but was also introduced in aeronautics and the other field where fatigue is important. And indeed, due to the availability, development of hardware and software of the computer, let's say, okay, it was possible to start later than around 30 years ago, the simulation of shot pinning. That is to say that how indeed, this is another important step, the ability to simulate the treatment itself and to simulate which are the results. Initially, in terms of
macro residual stresses, and then also in terms of hardening, we will see, and in terms of surface finishing, surface roughness. So initially with the finite element model, we've simplified approaches, so one single shot or a limited number of shots, and then later also with other methods that are able to consider the shot flow, I mean the discrete element method, another method that make possible the even a finer comprehension, finer understanding of the treatment. And what is going on? Indeed, the simulation and the other part goes on. The tool we have, the method we have for measuring for the experimental analysis, let's say, of course, are already in use and are improving and improving. But what is considering the evolution due to the so-called industry 4.0 or I 4.0, indeed, the new trend is to develop the so-called digital twin, that is to say, digital models that are able to interact with the physical plant. In such a way, we can improve the industrial process in real time, making possible, and this is made possible by the possibility to record a huge number of data, and then and it is possible also thanks to the model that we have to define, to simulate shot peening. Okay, and then another field that is under development is the application of shot peening to additive manufacturing part. Why? Because, as I said already yesterday, indeed, additive manufacturing is quite powerful for a design engineer. Is a great tool because it makes possible solution that once was considered efficient and so on, but just an academic practice, let's say, because it was not possible to get them in an industrial environment. Now they are possible. At the same time, additive manufacturing, the parts that are obtained by these processes are not ready to use as built. Why? Because the quality of not only of the defect they have, internal defect, and the quality of the surface is not enough, at least for structural application, for fatigue application. And so some post-treatment is needed, and shot peening is one of the possible post-treatment we can use for improving the fatigue strength. Oh, here I have reported some of the paper I wrote. I and my co-worker wrote about shot peening. The first date is this, and it was a finite element simulation, and was the first paper that tried to relate the Allman intensity that we will define in some minutes, let's say, to the residual stresses, okay, inducing compound part. Okay, so the aim was, if we know the intensity, we can determine, we can evaluate, assess, let's say, which are the final residual stresses in a component. And then, indeed, if you look at the titles, I also use shot peening not only for fatigue, but I explore, let's say, the possible application of shot peening also in other fields. One of these is the application in biomedical devices, let's say, that is to say, to improve the cell adhesion, the osseointegration for prosthesis, let's say, or to reduce the bacteria adhesion and to avoid so infection. With interesting results. Okay, and then also later, the work was done to explore what's happened if you are considering shot parameters that are more severe, let's say, than the usual one. And we call it severe shot peening. That is to say, we are using intensity or coverage that are more severe than the usual one. Why this is possible? To induce, to not only residual stress, but also to induce grain refinement. Okay? And here the key, the challenge is to have this positive microstructural modification without decreasing so much the surface quality. Because if you are using a higher intensity, shot peening intensity, it's also intuitive to understand that the surface roughness will be increased, of course. And so in the end, we develop also a method that reduce, alleviate this effect, maintaining the other ones. But let's see now which are the main effects, a bit more in detail. Okay, on the surface, if we refer just to the free surface, what we can notice is the roughness modification. Okay, that is indeed, if we consider, indeed, it's curious to notice that if we consider the traditionally machine, manufactured or machine part, the surface roughness at Torpini is increased because we start from generally, at least for very smooth surfaces. If we shot pin a crankshaft or a shaft or gears, indeed we start from very fine surfaces because this is what we want during this service condition. But and it's curious that if we start from additive manufacturing, this is not true anymore because the surface roughness of the as-built laser powder bed fusion part is poor. So the treatment must be completely retuned, let's say. If we go in depth and we consider not only the free surface but also the layer closer to the surface, we have also an increment in dislocation density. This is the second effect. And if we use what I said, severe parameter, this increment of dislocation is so huge, let's say, that we induce recrystallization and reduction of grain size. Or also, of course, this is also plastic deformation with hardening. This is a macroscopical effect that we commented that is due to the impact with enough kinetic energy. And about grain refinement, I said this can be obtained at least in a noticeable way, not just in a very thin layer of material where it is not used for severe parameter. And if we'll go even deeper, okay, we can obtain also, this is what so most important to say, is microstructural changes. That is to say, if we have austenite, this is true for especially for the steel that are used for gears, that are good for carburizing, let's say. If you are using this kind of steels that have a quantity of retained austenite, okay, after shot peening in the surface layer of material, this is transferred to martensite. This is due to the kinetic of the transformation, and this make stronger, let's say, more. So retained austenite measurement can be done with XRD, the XR fraction measurement. And if we go even deeper, this layer, indeed, we can notice also that the compressive residual stresses go down to 0.3, 0.4 millimeter with respect to the surface. Okay, this is maximum layer that generally considered the maximum layer that can be interested by shot peening. Okay, and just to comment here, this the free surface with the roughness that is well evidenced. This is some picture taken at the electronic microscope for evidencing the microstructural variation induced by shot peening, and this is a typical residual stress trend that we will comment not now, but later. Okay, we can move to the next presentation now. So let's go now. This is the subject we are dealing from now on, this today, and then also what can we see now? We will see two different aspects of shot peening, basic aspects, let's say. Which are the possible shot peening plan, the way we can apply shot peening with different plan, and so we will comment the two main way we can perform shot peening with centrifugal machine, or also called wheel peeling machine, or with pneumatic machine by using compressed air to accelerate the shot. These are the two main shot peening processes we can do. And then we will take a look, we will define which are the process parameters we should consider when we are defining the application of shot peening. So the media, which is the effect of the choice of the media, how the intensity of shot peening is defined. And as I said, we will refer to the John Allman definition of intensity. And finally, what is the coverage? These are the three main parameters that define the way shot peening can be done. Okay. I'm not repeating, this was a recall of the previous presentation, but we have just done, so no reason why to spend time there. Okay. Let's start with the wheeling machine. This is the principle you see. What can we see here? We see a wheel with some blades, okay, that is turning around the axis, and by means of turning is centrifugally accelerating the shot that are used. And these are the main part of the on a plant like this. The blades, the throwing blade are here. The shot opening that make possible the radial movement of the shot. The control gauge that define that control the movement of the shot, and then the impeller that accelerate the shot. And at the end, due to the rotation of the wheel at high speed, the shots are accelerated and then goes to the impact and impact the target material here. Okay, and what can we say? That the control amount of shots fall to the feet onto the blast wheel. The impeller run in synchrony, of course, with the blast steel, accelerate the abrasive, in this case the abrasive can be the shot, and deliver to the throw blade. Okay, and in this way, by adjusting the position of the outlet, we can control the shot flow. And here we see also how we can estimate, let's see, the projection of the shot, the way the shots are impacting the target material. So we should also define the distance we put the target material with respect of the wheel. This is a bit more complete scheme of the plant. What can we see here? We have open with the shot. Here is the blast room, the room that is used for shot peening here, and then the shots are filtered and they are repristinated by means of this polisher, and then go back in the cycle. Dust is removed, of course. Also damaged shot are removed, and this is the way a wheeling machine works. This is just a scheme. Of course, the plant is more complicated. Okay, but this is just to let you see how the wheeling shot peening machine works. Okay, you see the new shots are put here in such a way that the number of shots that are active in the process is not changing by adding this one and removing the damaged one. It's important to see that the number of blades influences the projection of the shot. You can see here the difference between a wheel with one disc and 4 blades, 6 blades or 8 blades. And you see that the projection, the area that is of interest for the shot peening flow is going to be narrow if you are using more blade. So what does it mean? It means that if you are using more blade, the effect will be more accurate. That is to say, the shot flow will be spread, will be distributed in a smaller area, and will be so. And so the impact with that part of the object to be treated will be with a more uniform impact condition. Okay, and finally, what you see here is this. This is a qualitative representation of the impact condition, impact force, let's say impact pressure of the shot along the projection area. And you see here that the shape can be considered almost as a Gaussian shape. Okay. So what's important to note is that with this kind of plant, by increasing the number of blades, the accuracy of the treatment is increased. That is to say that the pattern is concentrated in the central area. Okay? If we are using more than one wheel, so two wheels in this case, we are able to do even more uniform the treatment. Why? By using two wheels in such a way that the overlapping of the two projection is something like this. In this way, we have a central area that is almost uniform, and then the effect is going to decrease. And here you have, I don't know how much is clear this representation. Anyway, if you consider the curve with the same color, this represents the corresponding machine. That is to say, the black line, for instance, 1 and 2 here, represent the single projection area of the condition of the wheel, the two wheel with one disc and 6 blades, and the other black area represent the overlapping of that is much more uniform. Okay, so it's a qualitative, again, representation, but may give an idea of the effect of using a more complex plan with two wheels, but this makes possible to increase the accuracy of the process, at the same time to reduce the time of the process itself. Okay. Okay, some number now, indeed, which are the power, which is the power of a wheel shot peening wheel plant. Indeed, there is an empirical relation based on experience that we need 6 kilowatt for using 80 kilogram of shots per minute. It means that if we are using 100 kilowatt, we can deliver, let's say, we can use 1,200 kilogram per minute. This is give you an idea of the order of magnitude of the power we need and how this is related to the amount of shot we are using. And then the wheel arrangement. This is very important for this kind of treatment. Why? Because indeed, it's clear that wheel peening is not, we are not able to control the position very accurately. Okay, because there is the projection is spread, there is the Gaussian, and so the arrangement of the part to be treated is quite important to concentrate the impact with the right parameter, in the central part of the Gaussian pressure distribution in the right part. And here we can see what is here. Here is a shaft with a bevel gear here to be treated, and we see here different arrangement that refer to what? That refer to different details to be treated of the shaft. Okay? And you can see here that according to this different arrangement here, the rotation, the verse of rotation of wheel 1 and wheel 2 is changing from anti-clockwise to clockwise in this case. Just to give you an idea of indeed, what does it mean? That we must carefully design the arrangement of the treatment, okay? To treat the part where we want to, in the detail that we want to treat. Here in this case, it's probably the teeth of the bevel gear and some geometrical detail that are the most stressed part in a component like this with this bevel gear. And by means of these two applications, we are sure that we will get the right cleaning condition. Okay, of course, we should anyway perform the quality control, the check after the treatment to make sure that everything was well done. Which are the parameters that we can adjust when we are talking about the wheel pinning machine? We said the wheel position and angle, so the arrangement, let's say, the distance will be the wheel, the wheel and the target part, the workpiece, let's say, because of course the impact energy depends on the distance, depend on the initial condition, of course, but also on the distance, because we are losing during the flight of the shot, we are using second by second, let's say instant by instant, a part of the kinetic energy. The, the frequency control wheel power, okay, the power of the wheel, the angle of the control gauge, we are referring to the plant itself to make sure that the flow of the shot is the desired one. The direction of the, this may be trivial, the direction of the blast wheel, anti-clockwise or clockwise, and we must set the right way. The shot velocity, and it depends on some parameter, but the most important one is the wheel rotational speed, the shot quantity, the blasting time, how long is the treatment, to be sure that we are covering, adequately covering the area we want to treat, and the media. We will talk about the media later. And anyway, here I introduce some possible material for the cut wire that are harder, cast iron, okay, glass, ceramics, aluminum is not used. Indeed, for the media is important. What is the property we need for the media? The main property we need is that they are harder than the workpiece. Otherwise, the risk is that we are pinning the shots themselves and not the workpiece. So they must be harder than the workpiece. Okay, advantages and disadvantages of this treatment. Indeed, the treatment is controlled. We can control quite finely the treatment. It's flexible, of course. By means of different arrangement, we can perform different kind of treatment. The reliability of the process is high, is repeatable. Okay, so once it is the setup is done, we can run many times with the same result. Is also economic. Is economic indeed. There is a cost related to the plant itself, but then let's say the variable cost, the exercise cost, the cost needed for making the plants work are limited. Is considered as an economic treatment. Okay, it is used for large part and for mass production. If we need a high production rate, productivity, let's say, this is the right shot pinning process. Because it is possible to treat a large number, a huge number of parts in the working period, much more than for the other pinning processes. So the productivity, the production rate is very good. The disadvantage, the weak points are mainly two. The media flow is too large for small work pieces. If we need to pin small parts, this could be not the right way to perform shot pinning. And precision pinning applications are not feasible, or at least are not feasible in a very accurate way. Okay, that is to say, we indeed, the nature itself of the process make not possible to direct in the point we want some limited shot flow. So for precision pinning, maybe we have better option, let's say. But anyway, wheel pinning is largely used in industrial plant in mass production. If we want to pin gears for automotive, for common car, everyday cars, this is the way shot pinning is done. Some example of the process. Indeed, what can we see here? Here we see some springs okay, helical spring that are on this moving device, let's say carousel, moving this way, and everything has been set up, and so we are able, by the right arrangement of these two, we are able to pin correctly pin the spring in the treatment by means of two wheels. And the same here, this is another kind of spring. This is a leaf spring, as you can see, and this is not stress pinning. We are not applying a further load to increase the effect of film. It's just short pinning. And anyway, we can see here that by using an automized plant like this, making short pinning in a production line is possible and sustainable, let's say. Here is another, indeed, what can we see here? This part, this is not for accurate shot pinning, let's say. We have a series of parts here that are moved, rotated by means of these three rolls, and by means of the movement and the continuous shot flow coming from the two wheels, we are able, after a time, to consider that they are completely pinned or pinned in a sufficient way. Of course, this is more, this scheme is not good for precision pinning, of course. It's good maybe for more, if shot pinning is applied in a similar way to sandblasting. This can be feasible, but in a way like this, we cannot be sure of that, for instance, the residual stresses induced in the different parts are always the same or very similar, close each other. Okay. Here we have another possible plan. These are a carousel, a turning table with some conical spring that keep on turning this way, and by means of the two or even more wheels, we are able to get the pinning condition we want. And here you see a bit more complicated plan that is the part, the workpiece is the same as this one, but here we have an input line that is this one, a first wheel that pin one of the faces of the spring, then they are turned up and down 180 degrees, and the other wheel is spinning the other part. So this is also automized. And this example are just to let you see and understand that it's good for for rigid automated plants. This is rigid automation. The plant is developed for that kind of component. Okay, we are not talking about robot. So let's go to air pinning. Indeed, the principle is different. Okay, here we are using air to accelerate the shot, and we are using, indeed, here is clearly visible. What we have a nozzle here where the air, the compressed air, is mixed with the shot, and in this way we are able to, by means of this gun, let's say, with the nozzle, we are able to accelerate the shot. We don't need supersonic speed, let's say. The usual speed for shot pinning can be 60 meters per second, even less sometimes, 80, 90 meters per second. It's not usual to have higher velocity. Anyway, by means of air, compressed air, we are able to obtain this effect. Okay, so we have a control amount of shot that is accelerated in this gas. And indeed, here the trick is to arrange the treatment in such a way that the parameter, the compressed air parameter with respect of the shot we are using, are able to obtain the kinetic condition we want to get the desired effect, the desired residual stresses. Okay, and in this way, if you are using air pinning, it's easy to understand that this is more adapted to the application of a possible robot. We put the nozzle that is light indeed, it's generally light, it's not an heavy component, on a robot that can move and pin the different details even in a geometrically complex part. Okay, these are the difference. And here you can see a schematic view of an hairpinning plant. Okay. Okay, what can we see here? We can see here the different in the fan, the cyclone for collecting the shot. There is a sieve, the shot are sieved to retain and let go the right one and retain the other one. And then there is a series, and this depends of the plant we are using, of pressure and pressure vessel and pressure valves till the right condition. And finally, we have the gun that is mounted on a robot and a box, and the box where shot pinning is performed. Okay, we have a PLC board, of course, and the robot is controlled. Here, the ability is to the correct programming of the robot, of course. Okay, how can the gun be manipulated? We can have with different complexity way to manage the gun. We can have fixed gun with a dedicated setup, multiple nodes, and that are manually adjusted. Oscillator that are good for short stroke, for short movement, and can be horizontal or vertical, and the characteristic is that they are simple mechanism. Okay, and variable speed. Then we can have single axis mover or multiple axis mover. Okay, so these are more complicated. The speed is adjustable. And if we refer to multi-axial movement, indeed, the movement must be correctly programmed. And here we see some example. Indeed, the screen is not clearly video, but on the slide, I think, is better. The fixed, on the right, we see the fixed guns, and then going on the left, we have the single the single axis mover, and finally the multiple mover. Okay. We can also manipulate and move the part, okay, by means of the robot, not only the gun. And then we can have fixed spindle, door-mounted spindle, and today shuttle spindle, or today even more the robotic system. Move both the part and the nose. This make more complete and more general the possible treatment. By means of this a combined application of the movement of the part and the gun, and it is possible to have different conditions. And here we have some other example of this way and of the way we can manipulate. This is a blade, we can manipulate the part. Here is fixed. The blade is turning along the vertical axis. Here is the gun that can also move now. So I forget to ask if you have any question.
Sir, in that slide number 17, you were saying something about the oscillators. Slide number 17.
Oscillator, indeed. It means that we are using a gun that can move just for...
Will it dynamically oscillate, or like, you'll fix a particular SOD and then, you do the...
Dynamically, not high frequency, okay? They are dynamic, they are not static or quasi-static, but the frequency is in the order of hertz. Okay, this is what we mean with oscillator.
So while we are doing the short pinning process, this thing can move up and down.
Up and down, yes.
Okay, so will it not actually vary the residual stresses that is being induced? Because the distance is varying, will it not actually affect the residual stresses that is being induced?
At the boundary of the treated zone, this could be, but in the middle part, no. And this is in the detail we want to pin, that is the central part of the indentation area. Okay, this is not. That is to say, we are increasing the time, and this is after there is an asymptotic trend. That is to say, after a time, when the full coverage is reached, the residual stresses remain unchanged.
Okay. Thank you.
Yeah, right. Oh.
Hello. In the air peening, is it we are using abrasive along with the air or pure air, pure gas?
Pure air.
Oh,
We don't
okay.
want abrasive.
Oh,
Otherwise,
okay.
the risk is that we are damaging the surface.
Ah, yes, yes.
Okay.
So pure air and
Because if there is a sharp indentation, could act as a pre-crack.
okay.
And that
so,
is
so
bad
the
for.
so I'd like to know what is the cost of the
Do not
compressor?
confuse with water jet, where you need
Yes,
abrasives.
yes. So very costly because compressor units cost higher or like in comparison with other peening techniques.
Sorry?
This costly is very costly in comparison with other peening techniques.
It's
because-
more costly, yes, it's
okay.
but more accurate. So I will
Yes,
tell
yes.
you in a minute, but anyway, I can anticipate. This is good for accurate pinning,
Yes.
for part that deserve attention. It's
Okay.
not good for mass production. For mass production,
okay.
maximum wheel pinning is much more efficient and
Oh.
economically sustainable, let's say.
Oh, okay, okay.
Yes,
And
yes. No,
small-
I
small
agree
out-
with this observation.
This grain refinement will happen.
It depends. This could happen with both, but we need to increase the parameters. So
Yes,
the
yes.
time and the intensity.
sure. Yes,
Okay,
yes.
but it's possible with both.
Yes, yes, yes. Okay. Shock wave will come.
Yeah.
Right. It's like air shock waves will come, right?
So
Is it related to the shock wave? During air peening, shock waves will come. Shock load. Shock. Yeah. SHOCK. Shock wave. High velocity since it is comparable with this.
It's not a shock treatment, not shock. It's
Oh.
not laser pinning.
Ah, yes, yes,
Okay,
yes,
it is not a shock, a pulsed.
Yes, yes.
We don't. With shock pinning, we don't need a pulsed flow. This is
yeah.
needed for laser and also for water jet pinning
Yes, yes.
and for cavitation. We need the pulse. With shock pinning, we don't need the pulse and the shock. Indeed.
Yeah, because pure air is there, and it is.
We have a
it's traveling
dynamic
very fast.
impact that acts like a shock, let's say, but
Yeah.
the strain rate is not the same. It's not
Yeah.
the
Okay.
same.
Okay. Thank you. It's okay. Good. It's okay.
Professor, about this dual pressure, what is the effect of the single pressure and dual pressure? Why do we use dual pressure?
Where is
Slide number 16.
16? Yes. The single pressure. Indeed, could be only one, could be, okay. The two pressure stage are used for getting the desired pressure without making more complicated and the component themselves. So we divide the pressurizing stage into parts, okay? But it's not mandatory, okay? This is not mandatory. Okay, it's a possible scheme. Yes. Okay. So we have seen this or not? Yes. And these are possible arrangement of the nozzle. So we can have cylindrical convergent and then cylindrical nozzle, converging and diverging nozzle. Indeed, converging and diverging are not necessary. We are not at the speed of sound. We are much less than the speed of sound in this case. But anyway, they can be used. The cylindrical nozzle are generally used, let's say. Okay, this is straight or not used anyway. Okay, and we can also develop some special nozzle, like this one, to make possible shot pinning in details that are not easy to be reached. Okay, that is to say, we need some particular geometry of the nozzle to make possible to go in these small details where with the conventional, usual nozzle is not possible to be effective. Okay, and this is possible if you compare with with wheel pinning, this is an important difference. We can go in small details, intricate details, let us say, while with wheel pinning, this is not possible, or it's possible, but with very particular plans that no one is developing. Okay. And this is indeed a scheme of the design of the treatment, of the shot pinning treatment, to be performed by using air pinning. What can we see here? Indeed, the design of the treatment must start from the case assessment. We have a part, we know the application, we know the environment and the load that will be applied to the part, and then we start from this, the material of the part, of course, and we start from this statement. Okay, so the case assessment, what does it mean? We know the geometry, we know the material, the applied load, and from this on, we move on. Geometry, what does it mean? Shape and dimension. And in terms of dimension, it allows us to determine which is the nozzle number, okay, and the type and the shape of the nozzle, if we need particular nozzle or not. The same also for the distance, the same can be said for the shape. The distance is also another parameter that can be determined as a function of the geometry and the shape, and the angle of attack. Okay, the angle of attack, what does it mean? Indeed, which is the inclination of the nozzle with respect of the surface to be treated. Indeed, it's usually it's generally close to 90 degrees perpendicular, but small deviation from 90 degrees are also usual. Otherwise, the risk is that the pinning flow is spinning. There is an interaction, let's say, between the incident flow and the shot and the one that are coming. So that we lose a part of the impact because they are impacting the other pinning, the previous shot that have already impacted. Okay. In terms of the material, indeed, by knowing the material, by knowing the shape, we can determine what is the intensity and the shot and the intensity and the shot dimension. Okay, and this can be done also by knowing the applied load, and then if we know the load, we can also have an idea, an estimation, the determination of the applied stress. If we know the applied stress, we can calculate, have an idea of the desired residual stress we need, and then we can choose the right intensity, shot time, and finally the coverage. Okay, this is what the scheme of the design of the air pinning treatment. That is quite accurate. Indeed, we consider not only the part itself, but also the main point is this, is that we are choosing the parameter, the shot, the intensity, the coverage, as a function also of the working condition, of the service condition. Okay? And this can be done, why? Because we can control the way shot pinning is performed. So we can relate the expected residual stresses to the applied stress, and then we can develop the so-called optimal shot pinning treatment. Okay. So, to conclude the slide, a very fine design of the shot pinning treatment needs to know also the service condition, in terms of part, geometry, material, and applied load, to choose the right parameter. Okay, which are the adjustable parameters for air pinning? Indeed, the distance between the nozzle and the workpiece, of course, the direction of the shot flow with respect of the workpiece, the inclination, as we said, that we can program, 90 degree or something less. Indeed, we are not choosing generally very small angle, 40 degree, 45, 50, because indeed, in this case, we are losing a great part of the kinetic energy in friction and not in inducing residual stresses. But indeed, as I said, slight deviation from 90s are common to avoid the rebound of the shot and the contact between the incoming and outcoming shot. Okay, the air pressure, this is a parameter that we can adjust, we can control, of course, and determine the kinetic energy in the end of the shot. And of course, the shot type and material, so the dimension and the material, the velocity that is related to the air pressure and to the shot itself, the shot flow rate, that is the shot quantity, and the blasting time, the total blast treatment time. Okay. Also in this case, we can draw some main advantages and weak point also for this treatment. Okay. Indeed, the advantage is that air pinning is good in application that requires accurate targeting. In this case, we are able to perform a fine shot pinning. We can pin accurately the part, even small detail that we want to pin. We can pin just selected part and just those one. That is why we can cover just selected area by means of the accuracy we can get by using air pinning, a gun, and a control movement of the gun. As we said, this is good for accessing difficult geometry, intricate geometry, not all of them, but many intricate geometry, okay, and small parts. We can use different intensity on the same part if we need different intensity, and this can be done by changing during the process the pressure of the compressed air. Okay. Or at the same time, we can use simultaneous intensity on two surfaces, and by using also by controlling the pressure, we can use even light intensity. That is to say that we will do the scale n later, but anyway, n is a very light intensity that we can obtain by using light shot, that is glass or ceramic shot. Okay. The wrong point is not good for mass production. It now should be clear why this is not good. As he said before, indeed, the production rate cannot be as good as wheel pinning. We cannot arrange this carousel, this automatic plant. And of course, it's more expensive, sorry, for the type of than wheel pinning. Okay, this is what can we say? Okay. And so let's go to the describing the media. So the plants are done. The second point that we said is to define a bit more in detail, which are the process parameter, whatever is the pinning we are performing, wheel or air pinning. The media are the same, okay, of course. And the media are important. We choose the media with respect of the application we must apply. And a common point is, the first point is what I already said, that is, the media must be harder than the target surface, the workpiece. Otherwise, we are not inducing, we are not getting plastic deformation, at least not as wanted, but we are getting plastic deformation in the shot, and this is this is not what we want to obtain. Okay, and some comment about the choice of the control of the shot. That of course, is a primary factor for having a successful shot pinning. The characteristics of the shot are defined by the user and the media manufacturer, or also by international recognized sources. So if we need to have some the characteristics of the shot, because we must choose the right one, we can refer to the international standard in the end, or to to the paper, let's say, given by the producer, where we have the commercial shot, the dimension, the diameter, the material, the harness, and the process they were obtained from. Okay. The SAE, sorry, the Society of Automotive Engineers in the USA specification standard are widely used. Today are the most widely used. Okay, and the same applies in the special issue AMS for aerospace. Okay. J is another particular specification for general application. But let me say the most widely used are the general specification being given by SAE. Let's talk about the material. We can use different materials. Okay, of course, the shot have a cost, and the cost is varying with, of course, with the process we are using for obtaining the shot themselves. Okay, and the main property that we must guarantee is that the harness is larger than the one of the treated part, of course. Okay, the most widely used material for shot peening is cast steel. Okay, and the process we are using for cast steel is atomization. So we are using molten steel, and by means of atomization, by letting it go through an hopper, and by using water, finally we obtain spheroidal, not spherical, but spheroidal shot that are almost controlled, let's say. Then the shots are post-processed by heat treatment, and another process is sieving to collect the right one, the one with in the right dimensional range, and to retain not to use the one that are not regular with irregular geometry or in another dimensional range. The main mechanical characteristic of this cast steel shot are the harness that is around 45 and 52 Rockwell C grade, or sometimes even larger, but not frequently, let's say. Density is the density of steel, so 7 grams per cube centimeter. Okay, and this is the most widely used. The second one is cut wire shot. Cut wire shot, in this, the process we are using is, we have a steel wire and we are cutting in the wire in length, in equal parts with equal length, and then they are rounded and rounded with to remove the sharp edge, to make them rounded, spheroidal. Okay, these are more expensive. Of course, the process is more expensive than the previous one. And in this case, indeed, they are used because especially for where we need another shot, for other surfaces, because we can go to more than 62 Rockwell C. That is, cut wire shot are less used, and are used when we need another surface, another shot. Okay, then we have the steel pinning part that are similar to the previous one. The process is similar. Then we have to cut steel wire, and then we grind the cylinder in such a way that we are able to obtain finally the spheroidal shape. And we have a gradient trend of the hardness, and in the surface they are quite hard. Let's say 62 Rockwell C is the value we can obtain by means of this process. And then we have glass and ceramics. They are lighter, of course. The density of this material is much less than the steel. But they are, why they are used? They are used if we need fine pinning, let's say, and if we want to avoid possible contamination of the surface with steel. For instance, if you are pinning an aluminum part, okay, and we use steel, the surface will be contaminated. And if you don't want, for some reason, the contamination, because it's damaging anyway is the behavior of the aluminum, we need to use some other material. Glass or ceramic are the most widely used. If we refer to glass, the process is they are manufactured with high quality glass of the soda lime type and with a minimum silica content that is around 70%. The hardness is less than the one that we can get by steel. Okay, and the density is around 2.3 grams per cubic centimeter. Okay, as regards ceramic, we are using fusion of zirconium oxide, silicon and aluminium, and the hardness is better, is much harder, let's say, steel 63 Rockwell C. Okay, glass and ceramics are also used when we want to obtain light intensity. Why? Because due to the different density, okay, for a given velocity, the kinetic energy will be lower, of course. And in this case, so the energy that is available for plastic deformation is less, and so the final treatment will be less. Before going to the geometry of the shot, indeed, maybe someone of you have heard about ultrafine pinning, this kind of, where we are using a different kind of media for those particular pinning treatment. We are using media whose dimension is quite smaller. Okay, something similar to what? To the dimension of sandblasting, let's say, but with much more controlled shape. Okay, so we are able, and in this case, why are we using this media, ultrafine pinning? Generally for addressing shot pinning to intricate details that are not able, that is not possible to hit with normal shots. Okay, with usual shot, let's say. Okay, this is the reason why. And in this case, also the final intensity will be lower, but anyway effective. Okay, the intensity will be the one, the expected one. This is ultrafine shot pinning. Okay. Let's say now something about shot size and geometry of the media. Okay, because the material is, the choice of the material is good, but we also need to choose the right geometry, okay? And in terms of size and shape, of course. Imagine we are not changing, we are assuming to change just the shot size and geometry, okay, the dimension. Indeed, if all the other treatment parameters remain the same, the shot dimension determine what? The residual stresses and the surface indentation dimension. Okay, so the parameters are the same. If you are using different shots, also the final residual stress field will be different. And the same can be said for the indentation. This is due to the different contact zone geometry. Okay. And why we need to control the size and the geometry? To avoid that possibly sharp media are in the treatment, are in the loop. And in this way can be used and can hit the target material, the workpiece, damaging the surface. Something like this. It is not correct pinning treatment that is performed by using not acceptable shots with sharp angles, let's say. If the treatment is well done, this should be the surface that we obtain without any possible surface damage. Maybe in the slide here is not clearly recognizable, but the main difference, the difference between the acceptable shot and the not acceptable shot is in the second group we have many shots with not regular shape, with irregular shape. That that if used in the treatment would produce not some irregular indentation with possible that could act as a possible crack initiation site. Okay, this image is taken from the code, from the military code that now is adopted also in the in European standard. These are acceptable shapes, so we don't need that the shot is fully spherical. We can tolerate some deviation, but we cannot tolerate any sharp edge. And we cannot accept strongly deformed shape like this. Why? Because indeed, we can have contact condition in these cases that could damage the surface itself. And the same, even more, if we are considering broken shape like this. This is clear, the effect will be to produce a sharp indentation, giving in the end, giving a possible crack initiation point. And at that time, the benefit, the beneficial effect induced by residual stressing are at least partially, if not totally lost. Okay. And so, and now before stopping for the break, let's introduce the intensity and the coverage. These I need. The shot is it's clear with the effect of the shot. So another shot, indeed. We are choosing the shot with respect of the workpiece, the case we have to deal with, to solve. Okay, the dimension will be chosen according to the geometry itself. Let me add one thing that I forgot to tell you, indeed, which is another criterion for choosing the right shot dimension. Imagine you have a fillet, let's say, a fillet radius, okay, and you want to pin that detail. It's important that the dimension, the radius or the diameter of the shot is small enough to make possible that all the radius is hit by the shot. Otherwise, if the radius is more than of the radius of the fillet, the contact at the fillet will be prevented, will be not possible. So the criteria that not to be forgotten, of course, is that the radius of the shot, the diameter of the shot should be not less, but 1/2, let's say, of the radius of the fillet, in such a way that we are sure that there is not any geometrical restriction, geometrical constraint, let's say, that prevents the contact of the shot in the detail of interest. Okay, so the shot must be chosen, the shot dimension must be chosen with respect of the dimension of the detail we must be. Okay. Sorry? Break. Okay. Let me ask if there is any question, and then we can stop. Please.
Sir, you were saying that the velocity for this short pinning would be in the range of 60 meter per second.
Yeah.
So, and at certain cases, it can even go up to 80 to 90 meter per second.
Yeah.
So, at this particular velocity, there's every possibility that because of the kinetic energy with which it is impinging on the surface, some friction might be generated, and because of that friction, temperature might rise on the
No, it's not enough. It's not enough, and indeed there is a slight heating, but not enough to induce microstructural transformation, microstructural change.
Even if the exposure time for the short pinning is more, even then the temperature wouldn't rise.
Anyway, you have a flow of air. Whatever is the process you're using, air is flowing and is cooling down the system. No, this is negligible.